Gheens. So that's, I hope, a introduction that gives you some sense of what the LHC project is as a engineering project, as a physical object. Now I'd like to discuss what it does, what it is as a conceptual or teleological object. And here's what it is. It's an ultrastroboscopic nanomicroscope for studying deep inner space. Any questions? Now, let me unpack that a little bit. This is what our equations tell us we'd see everywhere and every when if we had nimbler eyes. In modern physics, we learn that what appears to our eyes, with their rather poor resolution in time and space as emptiness, is a very impoverished picture of what's actually going on in space. Our eyes were not designed to look at events which happen on time scales of 10 to the minus 24 seconds, or on length scales of 10 to the minus 13 centimeters, where we learn, when we study things, where the action is. But using our noodles and using these equations that are so successful in predicting the properties of matter, we can reconstruct what our eyes would see if they had been designed, or I should say evolved, to look at those distances and times. So here it comes, the deep structure of reality. Brace yourself. It's a lava lamp. What you're seeing here is a numerical reconstruction or solution of the equations, actually, of what's happening all the time and everywhere in space, where you have so-called quantum fluctuations or virtual particles that have energies that come and go, this kind of spontaneous activity. This is actually fluctuations in the gluon fields that hold our atomic nuclei together. And what we want to do at the LHC is get more refined pictures like this that resolve even smaller distances and even faster events, because we think that's where the most fundamental processes are happening. So it's really in the same tradition as Leeuwenhoek with his first microscope that looked at living things and discovered they were made of cells, or Rosalind Franklin later, who wanted to study the DNA molecules and couldn't use visible light. Visible light has much too poor a resolution to see structure of individual molecules, but used X-rays. If you ever have seen the actual X-ray pictures, they don't look like pictures of anything. They look like dots. They need a lot of interpretation. And that's what Crick and Watson famously were able to decipher, what these dots meant. The LHC is like that. But the image, since we're going to even more extreme conditions of short times and small distances, we have to do even more sophisticated image processing to get back from the debris of these collisions to what's actually happening in space and time. But really, what the LHC is no more and no less than an ultrastroboscopic nanomicroscope. It's meant to look at very, very short times and very, very short distances. And that's what we want. And just look at empty space. See what's there. Because we think, our equations tell us, that empty space has it all. It's reminiscent of the old concept of an ether, but much richer. I call it the grid. Everything that exists in real form, every particle that exists, even if it's much too heavy to have been discovered yet, is constantly coming into being and passing away on short distance scales and for short times in what we normally see as empty space. The heavier the particle, the shorter the distances and times, so the harder it is to resolve, but still it's all there virtually. The catch is that in our second golden age of the 20th century, we learned that seeing something is an active process. Ordinarily, when we look out and see something, we don't think that we're disturbing it, we just see what's there. But when we look at very small things in quantum mechanics, we learn that to see something, you have to do something to it. You have to look at it with a photon. You have to disturb it. This is encapsulated in Heisenberg's famous uncertainty principle. If you can measure something's position accurately, you have to sacrifice information about its momentum, its state of motion, because to see the position accurately, you need photons that have short wavelength, good resolution. That means they have a lot of energy and they can disturb the particle. In the extreme quantum world that we're talking about at the LHC, this goes a step further. Not only to see the things must you disturb them, like for electrons, but to see them, you have to create them in the first place, these new kinds of particles. They exist as virtual things, like lava beneath the surface of reality. To bring them out, you have to puncture a hole and let them spurt through. In that sense, bring them into reality, create them. That may sound rather mystical, but let me assure you that actual equations go with it. Specifically, for instance, to produce a particle of mass m, and the heavier the particle, the shorter the distance it's associated with. So if we want to look at really short distances, we want to think about very heavy particles, you have to supply at least the minimum energy, since energy is conserved, that that particle can have. And the least energy a particle of mass m can have is when the particle is at rest, and then it's Einstein's famous E equals mc squared. So the bigger the particle's mass, the more energy you have to supply to create it, to bring it into existence. And that's why when we want to examine really heavy particles, really short distances, we have to supply a lot of energy. And that's why the LHC looks like it does. To function as an effective ultrastroboscopic nanomicroscope, it has to put a lot of energy into a small place. Well, I've told you a lot of physics now in a short amount of time. Before the quiz, I think it's only fair to have a review. And I've prepared what I hope is a user-friendly review for you. And here it comes.
Oh yeah. I'm about to drop some particle physics in the club. The LHC is super duper fly. You know what I'm saying. Check it.
27 kilometers tunnel underground, designed with mind to send protons around. A circle that crosses through Switzerland and France. 60 nations contribute to scientific advance. 2 billion protons being round through the ring they ride, till in the hearts of the detectors that made it collide, and all that energy packed in such a tiny bit of room becomes mass particles created from the vacuum, and then.
Oh yeah.
LHCb sees where the antimatter's gone. Alice looks at collisions of red ions. CMS and Atlas are 2 of a kind. They're looking for whatever new particles they can find. The LHC accelerates the protons in the lead, and the things that it discovers will rock you in the head. We see asteroids and planets, stars galore. We know a black hole resides in each galaxy's core. But even all that matter cannot explain what holds all these stars together. Something else remains. The dark matter interacts only the buttons fill most of the known verse because CBC's where the antimatter's gone. Alice thinks in collisions of lead ions. CMS and Atlas are two of a kind. They're looking for whatever new particles they can find. Antimatter is sort of like matter's evil twin because except for charge and hiddenness of spin, they're the same for a particle and its anti-stuff. But you can store an antiparticle on any shelf because when it meets its normal twin, they both annihilate. Matter turns to energy and then it dissipates. When matter is created from energy, which is exactly what they'll do in the LHC, you get matter and antimatter in equal parts. And they try to take this back to when the universe starts, the Big Bang, back when all the matter exploded, but the amount of antimatter was somehow eroded because when we look around, we see that matter abounds, but the antimatter's nowhere to be found. That's why. CBC's where the antimatter's gone. Alice looks at collisions of lead ions. CMS and Atlas are two of a kind. They're looking for whatever new particles they can find. The LHC accelerates the protons in the lead, and the things that it discovers will rock you in the head. The Higgs boson, that's the one that everybody talks about, and it's the one sure thing that this machine will sort out. If the Higgs exists, they ought to see it right away, and if it doesn't, the scientists will finally say there is no Higgs. We need no physics to account for why things have math, something in our standard model went awry. But the Higgs, I still haven't said just what it does. They suppose the particles have mass because there is this Higgs field that extends to all space, and some particles slow down while other particles race straight through like the photon. It has no mass, but something heavy like the T-force, it's dragons, and the Higgs is the boson that carries a force. If the particles take orders from the field that is its source, they'll detect it.
Okay.